Alrighty, let's talk about some lipid anabolism. What we've got going on is we've got an excess amount of energy in the cell via carbohydrates, via protein, via fats. It's not really relevant where the energy came from, it's just that we have too much energy. Our acetyl-CoA that would normally be used in the TCA cycle to produce energy via the electron transport chain has built up to such a concentration that it cannot be kept within the mitochondria anymore. It therefore migrates across the mitochondrial membrane to be involved in the anabolic pathway of lipid biosynthesis. If you're interested in hearing more about that, you should watch the acetyl-CoA transport video. I screwed up a couple times, but you know, it all kind of worked out in the end. So, what we have right here is we have lipid anabolism. We can only really make one fatty acid in our body, and that fatty acid is in fact palmitate. Palmitate is a 16 carbon saturated fatty acid. 16 carbons, no double bonds. That is the only fatty acid that we can make in our body from scratch. Alright, so what's going to happen is we're going to have a certain amount of acetyl-CoA that needs to be transported across the membrane. Some of that's going to be made into malonyl-CoA. Specifically 7 are going to be made into malonyl-CoA. And then those two are going to combine together to form, palmitate and 7CO2. Alright? Each of these malonyl-CoA are going to lose one of their carbons. Acetyl-CoA is a C2 compound, malonyl-CoA is a C3 compound. So each of these malonyl-CoAs are going to lose one carbon dioxide off of them as they're transferred onto the growing fatty acid chain. Alright? Once we have our acetyl-CoA in the cytoplasm, it needs to be made into malonyl-CoA. Fatty acid synthase, which is this wonderful thing right down here, fatty acid synthase. Whew, I can't spell today. Uses both malonyl-CoA as well as acetyl-CoA synthase. Acetyl-CoA and malonyl-CoA as substrates for the reaction that it's going to do. So acetyl-CoA is going to be made into malonyl-CoA via a wonderful enzyme called acetyl-CoA carboxylase. This is another really nice enzyme. When you unpackage the name, it's working on acetyl-CoA. It's adding on a carboxyl group because we know that malonyl-CoA is C3 and acetyl-CoA is C2. So we know that it's adding on some kind of carbon group. You can say HCO3 or CO2. I believe it's in the notes as both. If you want somebody to argue that, I'll argue it for you. Carboxylase. Now, we are making a carbon-carbon bond. If we're making a bond, it means we need an input of energy. That energy is going to come from ATP. The hydrolysis of that high-energy phosphate bond is going to provide the energy for uniting this carbon here with the acetyl group to form malonyl-CoA. Alright, that is the first step in fatty acid synthesis. We know that there is an enzyme, a vitamin specific for this enzyme. Carboxylases are dependent on biotin. That is vitamin B7. Now, once we have malonyl-CoA and we have some acetyl-CoA in the cytoplasm, fatty acid synthase is going to start to work. So what we have here in red is our malonyl-CoA. What we have in black is our acetyl-CoA. The very first step of fatty acid synthesis, that fatty acid synthase is going to catalyze, is it's going to catalyze the movement of this group right here down to that sulfur bond. Now you're going to notice right away that we had acetyl-CoA and malonyl-CoA. Right down here, we don't have any more coenzyme A. The energy present in these high energy bonds right there, the malonyl-CoA, the acetyl-CoA, the energy created by the hydrolysis of those bonds will bind acetyl-CoA and malonyl-CoA to fatty acid synthase. The coenzyme A is required to create this bond between fatty acid synthase, so fatty acid synthase can work on both of them. Now, what we're trying to do is we're trying to make a fatty acid. And we know that a fatty acid, excuse this stylistic drawing, is literally just a chain, where each point here is essentially a CH2. There are no double bonds. At the very end, you're going to have your carboxylic acid group, which is going to be a COO-, but everywhere else you are going to have just carbons and hydrogens as we are making a saturated fatty acid. So what we need to do now is we need to make that carbon right there look like a saturated fatty acid. We're going to do that through 3 steps. Remembering that fatty acid synthase will catalyze a total of 4 steps, right? So the very first step is acetyl-CoA transport. This is exactly beta oxidation in reverse. Acetyl-CoA transport is the first step of fatty acid synthesis. It was the last step of beta oxidation. The next step is a dehydrogenation in beta oxidation. In this case, it's going to be again, a dehydrogenation. What we're going to use for that dehydrogenation is NADPH. For each step of fatty acid synthase, we're going to use 2 NADPH. One of those NADPH is going to be used to make the input of 1 NADPH is going to create this. The input of the second ADPH is going to cause a dehydration, which means that we're going to have H2O and CH2. Now, it's really good to keep in mind that if we are speaking 100% biochemically accurate, all of your electron carriers, NADH, FADH2, NADPH, are associated with 2 hydrogen ions. NADPH is technically written as NADPH plus H+. This isn't as useful here. It's a little bit too in-depth for the biochem that we need to go into to be a chiro, but it's really helpful to know that because each time you use an NADPH, you give 2 hydrogens to the molecule. That's why with the first NADPH, we made CH there and a hydroxyl group there. With the second NADPH, we added 2 more hydrogens to create CH2 and H2O. We've gained 4 hydrogens, although we've only used 2 NADPH. Now this is essentially just going to cycle through until you have palmitate. All right? So what is essentially going to happen is you're going to bind another malonyl-CoA on there. You'll have another acetyl transfer. You're going to use 2 more NADPH, and you're going to create basically just 1 more link in the fatty acid chain. So, really quickly reviewing my notes to see if I missed anything. It might be interesting to note that these are cysteine residues. I really don't know if that's relevant, but it's in there, so we might as well know. 2 carbons at a time. Oh yes, there we go. I knew I was missing something. As this transfers here, as each group transfers, you're going to lose a CO2. There we go. Our malonyl-CoA is C3. We're adding on 2 carbons each time. This is going to leave as the CO2 here. So bam. As this group is transferred sideways, the COO- is going to leave as this carbon dioxide. Now, this cycle is going to run, I believe, 7 times. We start out with 2. So if you start out with 2, the first cycle is going to give you 4, 6, 8, 10, 12, 14, 16. It's going to run 7 times. That means we need 7 multiplied by 2 NADPH. Which means we need 14 NADPH for this cycle to be complete. Now, we need ATP here in order to create malonyl-CoA. So we are making 7 malonyl-CoA. So we need 7 ATP for that reaction, for the reaction of acetyl-CoA carboxylase. Now, if we are including the fact that we're transporting acetyl-CoA across the mitochondrial membrane, you are going to require 1 ATP per acetyl group to transfer it across the mitochondrial membrane. That ATP is used by citrate lyase in the cytoplasm. If you'd like more information on that, look at the acetyl-CoA transport video. So in the case where we have an excess amount of energy from carbohydrates and we're getting our NADPH from the pentose phosphate pathway, we are going to use only 8 ATP to transport those acetyl-CoAs. In the case that we need NADPH from malic enzyme instead of the pentose phosphate pathway, we're going to be using a substantial amount more ATP. We're not going to go into that because that won't be a question on the exam. Van Fleet did not delve very deeply into the amount of ATP that would actually be used for this. It is sufficient to know that you would need 14 NADPH and 7 ATP in order to make 1 molecule of palmitate. Thanks so much for listening and watching, and if you have more questions, feel free to give me a shout.